Last episode we did multi-hop retrieval over the knowledge graph rag retrieval, and watched it answer a question that flat search couldn't reach. So here's the only question left. Do all 5 stages actually compose? Today we wire, package, serve, optimize, retrieve, and graph rag into one program and make it prove itself. You've spent this whole course closing one gap at a time: a packaged artifact, a served endpoint, a faster model, a retrieval layer, a graph. Each one was real on its own, but a system isn't a pile of working parts, it's the parts holding hands. The danger in shipping is the seam. Each stage works fine on its own. Then you connect them and things break in the gap. The artifact it doesn't match. The endpoint wants a different shape. The optimized model drifts by a hair. The retriever grabs the wrong chunk. The failure hides in the handoff, not the part. So the only honest test is end to end. So we don't trust 5 green check marks from 5 separate days. We write one function that runs every stage in order. It hands each stage's output to the next and checks one key number per stage before moving on. If any link is weak, the whole run goes red. That's exactly what you want a 3 AM alert to be: loud, early, and pointing right at the broken seam. One thing stays honest to the end: retrieval is real. FAISS finds the chunk, the graph walks the hops. Those are genuine algorithms on genuine data. Only the final language model step is faked with a fixed answer that's the same every time, so the run reproduces. I'll mark that in the code in one clause, the way I have all cores. Here's the capstone in one file. Build pipeline runs 5 stages top to bottom: log an artifact, serve it, optimize it, retrieve over FAISS and a graph, generate the answer, and returns a small status dict with one number per stage. Everything below it is asserts and a dashboard. Stage 1, package. We open MLflow, start run, fit a tiny seeded classifier, log param and log metric, and pull run.info.runid, a real MLflow run ID, the artifact's identity. Stage 2, serve. We mount that model in a FastAPI app and call it with test client, an in-process request that returns a genuine 200 without ever opening a port. Stage 3, optimize. We export the model to ONNX with a scale to ONNX, run the same input through an ONNX runtime inference session, and compare it against scikit-learn with np all close, parity true or the stage fails. Stage 4, retrieve, a real FAISS. Index FlatAPI over normalized vectors returns the top k chunk for the question, and a network's shortest path walks the multi-hop graph to confirm the entity chain. Stage 5, graph rag. We hand the retrieved chunk and the graph path to mock generate, which deterministically stitches them into one sentence. That's the single mocked clause. The real LLM call slots in right there. Every stage writes its headline number into the status dict, and the asserts at the bottom check all 5 at once. Run ID present, status 200, ONNX parity true, FAISS hit on the right chunk, graph answer 3 hops deep. Run it. Package logs a run ID and reports accuracy 1.0 on the held out split. Serve returns status 200 with prediction 0. Optimize reports ONNX parity, true max abs diff under 1e6. Retrieve hits chunk C3 at the top with the graph path Alice to service A to Postgres cluster to EU West, 3 hops, and the pipeline prints 5 stages green. The dashboard says exactly what the terminal says. 5 stage rows, each lit its own stage hue, each carrying the one number we printed. Run ID 200, parity true, top hit C3, 3 hops, and a single pink banner across the bottom, 5 of 5 green. The figure isn't a summary of the run, it is the run. That's the whole course in one green run. A notebook result became a shipped system, reproducible and end-to-end. You started not knowing how to serve a model. Now you've packaged, served, optimized, retrieved, and answered all in one chain you can rerun anytime. Go ship something.